it was not recording. Great, thank you. So the algorithm you do for this is you basically find a path in the graph from the source to the sink. So like, let's look at first, like on the very top path, you have an 8, a 2, and a 10. So this node has capacity 8, or this edge has capacity 8, capacity 2, and capacity 10, and you pump as much flow through that path as possible. So here, since we're essentially bottlenecked by this edge of capacity 2, we only pump a flow of 2 through this graph, right? So we say like, okay, this now has 6 remaining, can like be pumped through that edge. This nothing remaining can be pumped through that edge, and this that's a 0. This one 8 remaining can be pumped through the edge. But although this is like kind of greedy, we want like a strictly greedy approach won't work. So what we do is we create a residual network, which is essentially like which essentially allows us to undo these flows. So how we do this is we essentially say, okay, say we just flowed 2 units of flow from this node to this node, right? Which decreased like this edge's capacity from 2 to 0. What we can also say is, say we have an error, like a edge from this node to this node, essentially going backwards, right? This starts with a capacity of 0, right? We can't flow backwards. Why would we be able to? But once we flow 2 through this top edge, we can essentially say, oh, we can now choose to flow 2 through this bottom edge. Or sorry, once we flow through 2 through this top edge, we now have the ability to flow through 2 through this bottom edge, which essentially will counteract the flow through the top edge, because we're going to send 2 in one direction, and then we can choose later to send 2 back in like the opposite direction. So we're essentially counteracting the flow. And that's what that residual network allows us to do. So you can see that we just flowed 2 through this path, and through all the edges we flowed 2 through, we'll add an edge with capacity 2 in the residual network. Okay, so we continue the algorithm, right? We look for another augmenting path. We can take the one at the bottom, right? 10 to 12 to 8. This obviously has a bottleneck of 8. So like here, this will become flow capacity 0, flow capacity 4, flow capacity 2. We flow through here. Again, residual edges are updated. So this says edge 8, capacity 8, capacity 8, capacity 8. And then again, we just do the same thing. So out of the source, we can go take 6 flow this direction. We can take 2 flow this direction. If you notice, we could do like 6 flow here, and then 7 through here, and then 4 through here, and then 4 through here, maybe. So let's try that. Again, it doesn't really matter like what order you do this in, as long as you find a path and flow through it. So let's try that. We'll do this, which has an augmenting value of 4. So this will be decreased. This will be decreased by 4. This will be decreased by 4. And this will be decreased by 4. Again, we have to update the residual networks to allow us to flow that flow backwards again. So this is now 6. This is now created and made to 4. This is created with a weight of 4. And this is updated to 4. Notice how in every, or updated to 6. Notice how in every point in the algorithm, the sum of like the flow you can do in one direction plus this flow you can do in the other direction is equal to the original capacity total, right? And that should kind of make intuitive sense. Okay, so at this point, right, we have completely saturated this edge. So there's no more flow we can put in this through this edge. We can put a little more flow in through here. So this can take 4 more units of flow. But if you notice, both of the edges that move into like this node are completely saturated. So we can't put any more flow through here or through here or through here, which essentially means like we can't pump any more flow into this graph total. So what we're essentially left with, oh, we've pumped 8 through this edge into the sink. And what is this? 10 minus, we pump 4 through this edge. So I think that's 6. Yes, completely right. That's 6, because we have, yeah, it's just this value. So that's 14 total. And you can also just like look at any cut, we'll be proving that later, to find what flow has been pumped through the graph. And now if you notice, how do we know that we can't pump any more flow through the graph? Well, we kind of like looked at what edges were completely saturated, and at which point we said, okay, since no more flow can reach through like this edge or through this like line, essentially, there's no way that something can flow from the source to the sink because it has to go through one of the edges in this line. And that goes along with the notion of the min cut. So the min cut is basically a partition into two sets of nodes, right? One will include the source S and one will include the sink T. If you add up all the values going from, we'll call this part node group A and node group B, all the edges, the values of all the edges going from A to B, you can see here it's 2 plus 4 plus 8, which is 14. You get the value of the min cut. So what that actually represents in the graph is how much you can flow from A to B, like overall. And you can notice here that this min cut with value 14 actually is what bottlenecked this flow on our last slide when we were running Ford Fulkerson. So that's kind of the idea of why we analyze min cut. Right? We can take another cut, say like here, this is 9 plus 12, 21 is our flow across that, our possible flow across those two sets. But because there will always be like a flow or a cut with minimum value that will bottleneck the total maximum flow across the graph. And so that's why the value of our max flow and the value of our min cut is going to be equal. Does that make sense to everyone? Okay, so this is some new stuff now. So we're going to be talking about the flow value lemma, which essentially, one thing you say we have like this graph where we've computed the max flow and the values of flown through each edge. We know that to calculate or get the max flow from this graph, what we just need to do is look at the source and take the edges coming out of it and add up their flows. So like here, 3 is coming out of here and 8 is coming out of here. So we know there's a max flow of 11 total. Now the flow value lemma states that no matter what cut you take, the net flow along that cut will also represent the max flow. So here we have 6 going in this direction, 6 going in this direction, for a total of 12. And then we have 1 going in the other direction. A -1 gives us the same max flow value. So that will always be the flow of the graph. Now, how do we prove this? Well, we kind of do this in this like induction style technique. So we start with like S. We know that this cut because honestly, this is just a kind of cut into the graph into two sets of nodes, right? We have just the start node and then all the rest of the nodes. We know that this cut, the value along this cut, the net value along that cut will be equal to the max flow of the graph. Now, observe what happens when we add a new node, right? Say we, instead of just having S in our set of like nodes, say we add node A, okay? Let's look at the overall flow within this, that's coming out of this set and how that's been adjusted. So first of all, S, right? It had this 8 coming out of it into the rest of the nodes. That's still present, right? But now this 3 that previously went into the rest of the set is now going into itself. So this 3 no longer counts towards our flow total. So you can write like a -3 here. Now, to make up for that, we now have this edge coming out of the flow, right? Or coming out of this set. So now we have an edge of weight 6 coming out from this to all the other nodes, which means that the net flow along this graph is now added by 6, increased by 6. However, by adding A, we've also affected this, right? This edge is now flowing into our set of nodes, which makes the net flow by adding A decrease by 3. And if you'll notice, this just equals to 0 overall because of flow conservation. And we can keep doing this, right? So we'll add node B, right? And like this would be like 11 minus 3 plus 6 minus 3 is still 11, right? So we add node B, right? What this does, right? This thing that was this 3 that was previously forcing itself into our graph is now nullified. So that's no longer like a net loss in flow. So we can subtract it, or I guess we can add it actually. And then this 6 has now been added. Am I doing something wrong? Might be. Oh, no, I'm not. Okay, so this 6 has now been added coming out of our node cluster. So that's an inflow or like a flow out. We can add that here. This one's a flow in, so we can subtract it. And then if you notice, this edge of 8, which was previously flowing out of our set, is now within the set, so it's nullified. So we subtract this 8. And so, 9 minus 9, it's just 11. So essentially, what you'll end up seeing is that no matter how many nodes you add, the value of this cut coming out, or like the net flow across that cut, it's always going to be equal to the max flow. Okay. And then here's something that was mentioned in class. This is like, I just ripped this straight out of my notes, honestly. Now, if you have all like integer edge capacities, a few things will happen. Well, one, Ford-Fulkerson is guaranteed to terminate. It's kind of slow because you can sometimes get like funky setups that will cause it to like flip-flop. But at the end of the day, it is guaranteed to terminate. And because of the fact that your max flow and your edge weights are only being changed by a bottleneck every time, and that bottleneck is a capacity of an edge. Yeah, yeah. Because because flows across edges are only being changed by integers, because they're being changed by bottlenecks, and the bottlenecks are edge capacities, which are integers. The total flow and all flows along edges will always stay as integers. So that's kind of the idea there, right? We always increment by min edge capacities and adjust the residual network with those capacities. So as long as those stay integers, everything will stay an integer. Not sure how much you need to like know about that. I think that was on our last exam, but okay. And then this is new stuff. Actual applications of max flow. So a really big one is max matching in bipartite graphs. So say you have something like this, where you have a bipartite graph, which sets it up as like one group of nodes and another group, so two groups of nodes, and there's edges between the two groups. And you want to uniquely match up like nodes between the two groups, such that each of them are paired up without like two of them sharing something. So like there's no two nodes pointing to you or something like that. Each of them has like their own pairing from one node in this set and one node in the other set. So this is what's known as a matching. And to find the maximum matching, that is the maximum number of nodes that we can pair up from these two sets, we can actually use max flow. There was this definition of like a perfect matching where each node gets matched. Unfortunately, this can't be the case here. Not sure how important that is, but how do we actually use max flow to calculate this max matching? Well, what we do is we add a sink and a source, and we connect the sink to all the edges, to all the nodes on one end, and the source to all the edges or the nodes on the other end. And then what edge weights do we give each edge? Well, because of the fact that each node can only be used in one matching, we give each edge a weight of 1. So essentially we're saying, oh, we can pump 1 through to A, and then pump it out, follow it somewhere, and then pump it out through one of these nodes. But there will only be one matching coming from A and one matching matched up with U. Essentially, to make sure everything is only used once, we give every edge from the source and the sink a weight of 1. I think it also said in the slides that it doesn't matter what we assign these. So you can just say on like a test that we assign every edge weight 1 or every weight edge infinity, or these ones weight infinity. It doesn't matter because ultimately it's going to be bottlenecked by these ones. Okay, and then applications of this, other applications of this max flow. For one, it gives us the max number of disjoint paths with no shared edges. So this is similar to the quiz problem that said like, oh, if you run max flow, does it give you the max number of paths with no shared vertices? It wasn't no shared vertices, it was no shared edges. And the reason for that is, sort of intuitive, because say you have like a graph that's like this, right? If you run, say everything's like edge weight 1, because that's how you would prove this, like most number of disjoint paths. If you run the flow, right, max flow would be achieved by making this one of the paths and then the skinny path one of the paths for a max flow of 2, right? There's 2, because every edge has a weight of 1, each path, each flow can only use each edge. Each edge can only be used by one like flow, and thus only by one path. So here, this is like the counterexample for the quiz. So like, obviously the max flow is 2 here, but the number of like paths that don't share vertices, like it's only 1. But yeah. And then also, if you do the same thing, set everything up with edges weight 1s and then run max flow, you can actually get the number of edges to disconnect the sink from the source, or like disconnect the sink and the source, which is also fairly like intuitive. It's like here, since there's only 2 ways for things to flow into the sink, which gives us this 2 max flow, you can just chop it off and then they're disconnected. If we go back to like this graph, it's the same thing. Like here, if these were both edge weight 1, you'd get a max flow of 2, chop it off, and then like disconnect 2 edges, and then you're done. Yes, the max flow is the number of edges you delete to disconnect the sink from the source. Yes. I think integral flow might be this idea. You said it was brought up on the quiz. Which question are you talking about?
Basically about vertexes, joint paths.
Okay. Okay. Sometimes they just yap on those things. So I don't quite know why they said what they said, but I think integral flows is just saying like the flows are of integer values. So like there it's just saying like if you have a flow with like an integer max flow, like that will correspond to like a vertex disjoint path, because obviously like with the vertex disjoint path you can't have like 3.5 max flow and then like have like 3.5 paths. So like anytime they mention just like integral max flow, I think that's just saying like max flows with integers of values. I doubt you'll have to worry about it, like use it in an explanation or something. Okay.
So you said again, how do you find out like the no shared edges?
Okay, so what you would do, like say you just have a graph, right? Like this one. Say they give you this graph. What you would do, and this wouldn't have like edges, obviously, or this wouldn't have like edge weights. So what you would do is you would give each edge a weight of 1. And then just run max flow through this, right? So that would just give you something like, I don't know, this, for instance. I think that might be the only, yeah, that looks like it's the only thing it could give you. And that's how you actually just compute the amount of like edges or edge disjoint paths, right? And then maybe the other thing you might have to know is like the intuition for it. So for instance, like say we have edge weight 1 on here, right? And we add this path here to the graph. If we try to add like this path to the graph that uses this edge again, right? Note that like because of the fact that this only has edge weight 1 and all the bottlenecks will be of weight 1, once you get this path, this will be reduced to a 0 guaranteed, and then you can't flow another path through here. So essentially the only way to undo, you'd have to like go back from the residual and stuff. Essentially, each graph will only be used for like one total, or each edge will only be used for one total augmenting flow, which ends up being the unique number of like disjoint paths. I think it's like the number. Are you asking for like the answer? I think it would be like the number of paths. Yeah, just 2 paths.
Where are you going?
What did you say? What'd you say?
Well, let's see. Alright, I mean, you're straight, dude. I'm gonna start sliding those.
Yeah, I don't think. I'm just gonna mute. Just mute.
Yeah, no.
Okay, sure. You can say something in the chat if you're actually saying something. Sorry, in that case. Is there anything in the chat? There is. Can you record this? Your wish has been fulfilled. Okay, and then we'll move on to the real new content, the state machines. I made this the dark background so I could paste stuff from the new slides into this without having to worry about like the backgrounds not matching. So the first thing we learned are DFAs, right? The finite automatons. And so this is like the formal construction of them. I don't know if he'll make you like write this out on the quiz. It would be kind of annoying if he did. It was like one of the homework problems that made you do it. I don't know. It's probably good to know. Basically, these have a set of states, like an alphabet, a function that given a state and the letter currently on the state will give you a new state. So just like this, a starting state and accept states, right? And then we use terminology for recognition, essentially saying like, if you have a string and a machine accepts it, then you have like a language and the machine accepts every bit of that language, every string in that language, that machine is said to recognize that language. Also, probably not going to end up being super important, but probably good to know. And I did things a tad bit out of order here, but essentially, now we'll move on to regular operations, right? You can have languages, right, which are just sets of, or like here, up until this point, they're just kind of like arrangements of characters, but what we can do is we can union them, concatenate them, and star them, I guess. I think it's best shown through the examples, right? Union is basically saying, say we have a language of like certain strings. If we union them, we'll accept both the strings from either language. So this is essentially just like an OR. The concatenation like literally does what it says. It takes every single combination like and just concatenates them together, right? And the star or a star is literally just like given one of these, you start with the empty string and then you just add as many of each string in the language together as much as you want. So it's infinitely large. And for me, like this kind of was easier to conceptualize. Like if you ever use like something like regex, you know, like you can have like the star represent like, infinitely many of a certain character, right? That's essentially what this is doing. It's saying of the strings in this language, which, maybe it's just like, zeros and ones, you can have infinitely many of these. A equals, so a star could be like, you don't care, it could be like 0, 1, 1, 1, 1, 0, 0, 1. Yeah. And so I think it'll make a little more sense what these each do when we actually prove them. But before we go into proving them, or proving, sorry, not them in themselves, but that they're actually regular, we'll talk about NFAs. So the main thing about NFAs is that they're non-deterministic, which previously, when we had a machine, right, we say we had one state, and we were at a certain character, say A, we would move to another state. Well, the thing about NFAs is that they don't necessarily just have one outcome at a certain state. What they instead have is they can have multiple outcomes at a certain state. So the transition function, instead of just being like, you're given a character in a state, give me another state, it's given, you can essentially branch to multiple states from one state. And the idea is that even if only one of these is accepted, so like this can be an accept state, even if only one thread is accepted, the string that was input is accepted overall. And an important point is that these can actually be converted to the DFAs. And so how this actually works is your starting state is the same, or at any point, what your states are is a set of possible states in the other machine. So say this is our starting state, right? We would start with like Q. We'll call this one Q. And we'll call this like, I don't know, C and D. If we start at Q, and then we take an input A, or character A, we then can be in both the states C and D, right? So essentially, instead of storing states, we store groups of states. So we start with just the starting state in our group, right? And then at any point with all the states in our grouping, so it first starts with just our starting state, we look to all the possible transitions from that state with our given like character, and then we insert those possible states into our new state. Essentially, like here, we have Q, say we're at character A. We can move to either C or D, so our new state will just include C or D. If it was like Q, I don't know, Q, and then like C, and then say like C, led to another state that was like E, what we do is we say, okay, what can Q lead to? Q can lead to C or D. And then what can C lead to? C leads to E with, say this is transition label A as well. So essentially for every state, we look at all the possible next states. So we compile this huge list of possible states, which we can be in after like n iterations. And then this is just something like, oh, the states in the new machine is just the power set of all the states in the old machine, essentially every single possible combination, because that's just how it works. And then an interesting thing here is that like here in your set of possible end states, to be accepted in this new machine, this DFA, only one of the states in your like collection of states actually has to be in the like old machine's accept states. Because again, the whole idea is we only need one thread to end up accepting the input to accept it overall. And so this gives us a toolbox to prove that these properties or these expressions are closed under regularity. So essentially, if A1 and A2 are regular, then A1 union A2 is also regular. So the easy way to do it is just using an NFA, right? And then we just have a start state, and then we just add this epsilon edge. And this epsilon means like you can take it at any time. It doesn't require a value. So essentially, say we're given like the input 1, 2, 3. We can take this transition, and then we'll still have like 1, 2, 3 to work off of from this. And then, yeah, the idea for OR is basically just have a DFA. You have an epsilon edge from the starting edge, and then this is just like each of your machines, right? Essentially, you run one, you run the other, like they're both combined. And if either accepts the input, you're chilling. And then like the old way we did to do this is kind of like similar to what we did here, where essentially instead of having like an infinite number of states, or like instead of like having like, yeah, an infinite number of like states you can be at, you're always going to be at like one state in A1 and one state in A2, right? So what you're essentially doing is you're applying a new character to, you have pairs of states that you're starting at, and you're applying a character to each of those old states to get, a pair of new states. And then if F is in either, or if either of those, if you finish iterating and either of those two states are in the end state of the corresponding machine, you're chilling, the whole thing gets accepted overall. And then A star just works by your new starting state, we'll call it Q, is an accepted state. And then you say you have your machine. I don't know, I'll just make a square. And then anything, actually, I won't do that. Anything that like is an accepted state within that square has an epsilon edge to the old starting state, not the new one. So what this essentially allows us to do is like start here. Nothing, because A star accepts nothing correctly. So this is accepted by this accept state. And then say like our language is like A, the letter A, and A star is just as many A's as you want, right? You can have one A, and that will trigger this. Or you can take the epsilon edge, another A will also be accepted, a third A will be accepted, so on and so forth, right? And it's very important that you have this distinct start state. I think that was one of the questions on the quiz as well. Why can't this just be accepted? And that's because sometimes you do have like things that are only like half way and they loop back to the start state and then it just gets messy. So you do need this separate start state to accept the empty string. And then A1, A2, this is just like you have a machine and then all of the accept states from this machine will just like lead into the start state of the second machine. And obviously these are epsilon edges. And why we need non-determinism for this, because like we can't tell when to actually move iterating on this machine and like move to the next, the A2. Okay, does that make sense to everyone? I know I kind of rushed through this last one especially, but chilling? Okay. Yeah, let me draw it out. That was kind of like a oversimplification. So say, what's a word? Let's say we have like cats. What's a word that starts with S? I was gonna put like snake, but sure, that would work too. Like, so say A1 recognizes both like cat and cats, right? So we'll have like A1 here, and this will be like C, A, oops, T, then S, right? So C, A, T, S, this is accepted, and this is accepted, right? And then we can have this other one, which say will like A2 will only accept like snake. So we start and then we go like S, you get the picture, N, A, K, E, and then this is accepted. The idea is, say we have just an epsilon edge on this end, on like the end of the machine or something, and we take the CATS, take this over, you require a second S to be accepted overall. But if we take from every accept state an epsilon edge, I think this is what you were talking about, right? We can do like CAT, and then we can either use the S here, or move over here and use the S here. If we use the S here, we end up accepting. If we use the S here, we like terminate here. Is that what you were saying? Yeah. Ultimately, like for every accept state, you want to draw an epsilon edge to the next start state. Yeah, I can post the slides in like the Slack. Okay, yes. Overall, so A1, A2, this will accept both cat snake, right? Because it will go CAT and then over here and then snake, but it will also accept cat's snake. right? Because it will go 1, 2, 3, like cats, and then here, and then snake. So essentially the idea is like here, you can't jump like here after you put cats, but you can jump after cat and then do snake. And then here you can jump after cats and do snake. So in this case, any combination of these words and then these words will be accepted by the machine. And that's only because we have epsilon edges from every single accept state. Essentially saying we can transfer to A2 from here, and we can transfer to A2 from here. Sorry, what? Epsilon? Are you, okay, I think what you might be referring to is the, yeah, maybe the A star, like representing the empty string and needing to have a separate start state, maybe? Doesn't look like it. Yeah, this is like this is machine A1 and this is machine like A2, and we've concatenated them together with these epsilon measures. Yeah, every accept state in here just bound to the start state in here. I hope I don't like get something wrong here and then everyone is confused. Yeah, what's up? Is that for A star? Yeah. Yeah, so that is what I was talking about with A star. So for A star, yeah. So for A star, it's very important that you have, I'll just go over it real quick. Actually, what was my like, I think I have it in my notes. Yeah, that's when, yeah. Yeah, I have something in my notes about this. So say you have like a machine which has like a starting state, a Q, and then say you can take like 0, and then like if you end on a 0, it's accepted, and you can take like 1 and it goes back to the state. If you want to A star it, right? You might just think like, okay, make the start state an accept state, keep the, and then from every old accept state, just draw an epsilon edge to the new start state. Why this doesn't work, right? Say we have the value 0, 1, right? Here in this machine, this is not accepted. In this machine, it is, even though this is not like an A star of things that work, essentially. Right, is that what I said here? Yeah, 0, 1. Whereas if you were to add that separate start state, have that do an epsilon edge to this starting state, and then work from there, you can see that move here, 0, 1, it'll end up here, which is not accepted. So that's why you need to have that separate start state for A star.
So which one of those works? So that one works. One of the past.
Yes. Yeah. Sorry? We'll just say it's like 0 and 1. Oh wait, no, that's not the language, is it? The language is like it's stuff ending in like zeros. Yeah, it's strings of zeros and ones that end in zeros. Which I guess would that even like this wouldn't even be an A star, would it? Yeah.
Showing is that 0, 1 is not supposed to be like. But by making the start state an accept state, 0, 1 is accepted, which it's not supposed to be.
Yeah. Sorry. I confused myself. Yeah. Yes, 0, 1 is the alphabet. The language is stuff that ends in 0. I've confused myself. But yeah, I think there might be something weird here. But essentially know that because you can sometimes go to the start state by taking this epsilon edge and instead of taking like one of these edges, it will screw things up. Okay, are we ready to move on? So we can actually convert regular expressions to NFAs. This is pretty straightforward. Essentially, we have these methods to convert machines, right? Say we have like one regular expression, like two regular expressions, R1 and R2. We know how to turn the machines into like, R1 or R2, like union them together. But what about like adding extra things to the regular expression? Well, it's pretty straightforward. If you have like something that a regular expression that like accepts everything, or like it's just like this, then it's just like an accept state. And then something that like, accepts nothing, it's just a normal state. And then if it's just like, accepting A, then it's just the pointer to A. For instance, if you had like, A1 union epsilon, maybe, you could just be like, start state. Like we said last time, it's a union. We just need 2 epsilon transitions. And then, this epsilon would just be an accept state. So because it's like union, it would like always be accepted. So this would be like whatever A1 is. Yeah, and this kind of just shows that like if you have a regular expression, like the language it represents is gonna also be regular because you can represent it as an NFA, which means you can represent it as a DFA, which means it's gonna be regular. And then we can actually, do this the other way around as well. If we have an NFA, we can convert whatever this is representing into a regular expression. And how we make this how we prove this is by defining a generalized NFA, which allows regular expression as transition labels. So for example, here, you can have a label instead of just like one value, it's this. And the way we can, and obviously like at this point, right, if it's just like if this is like the accept state and this is the start state, this is obviously just like a regular expression in itself because it's just a machine that will like use the regular expression to determine like the output, right? So the way we do this is we have like this machine with all the like simple edges, and then we can combine things together, right? So say we have this, and it's like this is R1, this loops with R2, and then this takes like R3, and this is R4. One thing to note that's interesting about like this R2 infinite loop thing is essentially it means like you can have R1 and then as many R2s as you want, and then R3. So what that effectively is saying is you have R1 and then R2 star and then R3. We'll make this the accept state. And then again, here it's like you can either have R1, R2 star, R3, or R4. Both of them are accepted. So we can literally just like write it like this. We can say, oh, it's R1, R2 star, R3, or R4. And then once we literally just have like starting state, accept state, one transition in between them, like that transition is just our regular expression that represents the NFA. So yeah, every like machine you can just convert it to an expression. What's up, Frank?
Happens when we have an edge going from X to Q1.
Like this, you're saying? Well, what this would do is so you can have essentially as many R1s as possible, or as many R1s as you want, right? And then you can have as many R2s as you want. And then you could go back to the initial state and do it again. So I think this is what you'd end up having. It's my 2 cents. Sorry. What'd you say? You said R1, repeat that? One thing this does miss is you can take as many R2s as you want. So maybe like this. And this is like an epsilon edge, I think, right?
No, it could be any edge, be any.
Okay, that would complicate things.
Yeah.
Then yes, you might have a more generalizable thing actually. I like that because essentially you're taking R1 and then you can either take the new thing and do R1 again because R2 star can happen as many times as you want. Yeah, yeah. Sorry? Oh, you're right. Oh my God, Brian, why'd you have to ask me this question? I don't. Yeah, no, that's also correct. I don't know. It would. Yeah, yeah. I'm sure you could have figured it out. I think this is a good start. And then yeah, also you can do R4 from it, so it just turns into a nightmare. Yeah. You could yes. So you can transfer any NFA to a DFA, right? So essentially like what we've proved here is like the regular expression is like equivalent with an NFA, right? And then the NFA can also be converted to a DFA. But I think it's also fair to argue that like the DFA like is an NFA. It just doesn't use any of the NFA stuff because DFAs are kind of like subsets of NFAs, maybe. So they can all just kind of be converted interchangeably. If you have one, you have the other two. You're saying this one? Yeah. So this one is like this is essentially the regular expression, right? And then to get the NFA from this regular expression, you would have to like unfold it, which would give you like this. And then you could use the technique to convert NFAs to DFAs, and then you would get the DFA for this regular expression as well. So yeah, you with a regular expression, you could get a DFA. Okay. Let me like pull up the chat on the screen. I can see it. You think of pumping lemma? Did he say, I know you sent me, did he say that pumping lemma was going to be one of the, I think we could talk about those after. Yeah. 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 But so okay, pumping lemma, I feel like is one of the things it's like not that bad, but like it seems like one of the most trickiest things. But it's not actually like that bad. You just need to like know how to exploit it essentially. So the idea here is that this lets us see if languages are regular or not, right? If they can be represented by a machine or not. So if we have a language like A, we'll just call it like A, there's a certain value, I think this is called like the pumping value or something like that, pumping distance, where if you're adding more characters onto a string in that language, it's going to force a loop in the machine representing that language. And because of the fact that like, so the machine can only have like so many states, right? Which means that if you have a string that's accepted by the language, but it's like, less than that combination of states, like there must be a loop somewhere. And then that's where this idea comes into play, right? Where you have y to the I. So you get up to like a certain state and you start looping, and then you continue with z to an accept state. So essentially, past a certain string length, you're forcing a cycle for any like machine, because the machines can only have so many states, like a finite amount of states. Oh, I guess that's why they call it a finite state atonement. So how do we use this? Well, we can choose. So we're trying to prove that a language is irregular, right? So what we do is we choose an S, a string, in a language A. And this can be any string, right? You only have to do this for one string as long as that string works. And so this string has to have length over p. A lot of times you will be like using the fact that it has length over p in combination with this to like force your y to be something, but we'll get to that later. And we want to turn S into the form x, y, z, right? The two things to note: S cannot, or y cannot be empty. So y has to be at least one character long. And then y is also within the first p characters of S. So we can't loop things within like after p characters. Whatever you're looping has to be within the first p characters. And like you can, I'm not going to go over it, but you can like conceptualize that in terms of like how the machine actually is built. And then we want to show that for any number of repetitions of y, that or like for a regular language, no matter how many times you repeat y in that string, there will be a the resulting string with as many repetitions of y as you want will still be in the original language. So how do we disprove something? Well, we have to choose a certain S. We get to choose, but we choose an S that's in A, must be in A. And we show that no matter how long y is, because like x, y, z, this is a pretty broad definition. We just have to adhere to these two principles. No matter how long y is, right? You cannot choose this. This is has to be like you have to check all cases of this. No matter what y is, there will be like a number of repetitions that makes a expression that is no longer in the language. So we'll move, and yeah, you can also use it with closure properties. There's an example. I have some examples here to prove like stuff is regular or irregular. So we'll start with this, right? 0 to the k, 1 to the k. Now, we need a string that's in this language, so a string that exhibits these properties, that is over length p, right? And, it might seem daunting, like, okay, how do we pick a string at first? The whole like key of proving something is irregular. You just want to like exploit this property here. The fact that if that y has to be within the first p characters of the string. So here, what's the key? The key is that there's an equal amount of zeros and then ones, right? If we force y to be within that section of zeros and we start repeating it, then we throw the zeros and ones off balance. Because of the fact that y needs to be like greater than one character and it's guaranteed to be a zero, we're gonna like add an extra zero, at least one extra zero, no matter what y is, and then we'll have more zeros than ones. And again, y has to be within the first p character. So all we have to do is say, okay, it's 0 to the p and 1 to the p. This is a string within this language. And you can see that when we try to pump it, y will have to be within these first p zeros. And when we pump it, y will like some extra zeros will be added. And then whatever this is not going to be in here because it's more zeros than ones. Does that make sense? Uh, okay, not really. The idea is with like pumping is that once you like found what your y can be, right? You start repeating your y, right? And the idea is no matter how many times you repeat this y value in the original string, like that resulting string will still be within the original language. So here, right, like y will be within these zeros. And so say we have like, say p is just like 3, right? Say we choose like, this is our x, this is our y, and then this is our z. What pumping y means is that we can like add more copies of y, and what that results in is like this adds 2 extra zeros, right? And you can see that this resulting thing does not have an equal number of like zeros and then ones. So it's not in the original language. Then, so you're saying like maybe there's x is like this, right? And then y is just like this 1 0. In that case, we would just get like 4 zeros. Now, you might say, okay, what if y is no zeros, right? In that case, we would have equal numbers of 0 ones. That's why this is here, right? To make sure that y will always have at least one character in here. So we can use that to kind of throw the original rule off balance in the resulting string. What's I going to say? I forgot what I was going to say. Yeah, and one thing to note is like when you're proving this, you can choose whatever a you want, and like you only have to, so you can only have to prove it for one s, and you only, so I said a, you only have to prove it for one s, and you only have to prove it for like a certain amount of repetitions. But y, you have to show that for every single possible y, this will, you know, break the original like machine, or this will like not fit in the original language. So like here it's saying, well, I don't know what it is saying, but here, right, we prove that like y has to always be zeros. No matter what y is, it's always zeros, which means it will always throw the original condition off balance. And so that's how we know we've done it correctly. We'll move on to the second example. So this is WW, just 2 of the same string back to back. So again, we want to exploit this condition, right? If we can force y to be like a certain thing, and then repeating that certain thing will not put it in the original language, then we've done what we wanted. So, you know, how do we force y to be a certain thing? Okay, well, we just make something like p large, right? Now we know y has to be a 0, right? If we want 2 matching things, we can just like do what they did down there, which is 0 to the p1, 0 to the p1. The idea here, since y has to be within the first p characters, it's always going to be a certain amount of zeros, right? When you add more zeros here, these 2 items are not going to be equal. You'll have like 0 to the p plus x, you know, zeros, and then a 1, and then 0 to the p, and then this 1. And then these 2 are not going to be the same because x can't be 0. Does that make sense? Yeah. 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 So this one's saying you can't choose all zeros. That's exactly what this is saying. Because if you had like, you know, 0 to the p, 0 to the p, these are like our w's. And then obviously y has to be zeros because it's in the first p elements, which are all zeros. If you pump it, it may just have, it's still like all zeros, right? So it still can be like, you know, split it down the middle. It's 2 of the same thing. But if you have these like ones here, as kind of like markers of where your two equal W's have to be, there's like an obvious shift that throws the whole thing off balance. Because what'll happen is like, it'll be like, oh, one W is all zeros and one of them is like 1, 0 to the P1. Actually, there could be like zeros here as well. But point is, one of the W's is all zeros, one of them won't be. So you can't, yeah, you can't just use zeros. So I think that's where the issue comes in. So you can't choose which Y to use. So effectively, you have to prove that no matter what the Y is, pumping will break the system. I think, can you, Sai, do you know if you could choose? Sorry, I hate to put you on the spot. Any number of repetitions? Yeah, yeah. Do you know if you can choose like a certain amount of repetitions, or do you have to show that like for any number of repetitions it will break? I think it's like if yeah, yeah, yeah. So you're saying that like depending on, so yeah, you'd have, if you have a Y, say it's all zeros, right? If you have a Y that's, or yeah, a Y that's length like odd, if you pump it once, that will break things. If you pump it twice, that will fix things, correct? Yeah, and then if you have a Y that's even, if you keep like it will always work, right? If you pump it. Yeah, yeah. So the idea is a certain amount of repetitions. Yeah, yeah. No, I see what you're saying. Wait, let me check if it is the case that you can like this thing really is the case that you, because I'm not sure if it has to break for like all sorts of repetitions. I feel like it doesn't. I feel like it may only have to break in certain things. But yeah, okay, yeah. The idea, I'm pretty sure if it breaks like with any number of repetitions, you cannot use that Y to like make it regular. But the idea there is like if you have a Y that's even, um, it'll still work fine, right? So overall, you can't use that to prove it. Because what you're trying to effectively do is like say, I have this string, I want to like input it into the machine. And if the machine can like properly loop it in a certain way to give me the output, like then it's regular, right? So if you have a Y that works, that effectively means that the machine can have like the X and then pump the Y as many times as it wants, and that will always be accepted, or that will always like work fine, and then have the Z, and then that whole thing will be accepted by the machine properly. So yeah, I think if there exists a Y that works, you can't use that S. Essentially, you want to say like no matter what Y you have, it will break. Uh, it will like break if you repetition. I you're saying like yeah, you're saying there only needs to exist one possible Y, and then if that I think it needs to be for all possible Y. Let me see.
You get to choose like a string that will force X and Y into a situation such that all possible Y values. Uh,
Was there a something on the practice exam?
you just could not choose like the repeated zeros. Because there are some like choices for y that would work, but there are some choices for y that wouldn't work, so it's not enough to say, you know, here's a string, let me pick this particular x or this particular y.
Yeah, I'll pull up the slides, hold on. But I'm fairly certain it is just. Uh, Okay, okay. Actually, we just need to look at like the definition of the pumping lemma, I think, to resolve this. So this is saying, for if a language A is regular, right? There exists a P, and there's like some way to break it where for every number of pumpings, this is in the original language. So number of pumpings, if one of them breaks, like your whole thing will break, right? Because this is saying for every single I is greater than 0, greater than or equal to 0, it has to be in the original language. So if one of the pumpings is like, if you pump it a certain amount of times and that's not in the original language, like that won't work. But I think this is saying you can have a divide into X, Y, and Z where like this is true, then it's regular. Because if you, yeah, yeah, because I think if you think about it like that like 0 to the P, 0 to the P thing, like will still satisfy these two or these three things, right? There is like N I, or there is like a Y where this will work. Yeah, I'm fairly certain it's just, yeah. So yeah, this is the number of repetitions. This is like I has to be true for like it has to be true for every single number of repetitions, which means that you can just like have a certain repetition that doesn't work and the whole thing doesn't work. But like I'm pretty sure you have to prove it for every single Y. Really certain. If I'm wrong on that, you can blame your points lost on me. Unfortunately, I can't do much more than that. Okay. We'll move on to the last example, which actually utilizes the closure properties as well. Exclusively. They use the closure properties exclusively. And this is actually like a kind of interesting way as well. So back here, we proved that 0 to the k, 1 to the k was irregular, right? Wait. Okay, yes, no, sorry. This doesn't use that. This says 0 star, 1 star is regular. Why is it regular? Well, it is. No, I was gonna say I drew a machine in Slack. That's something else. But yeah, okay, this is regular because it's literally just closure under like regular properties, you know, like very straightforward, um, you know. But this is regular. Sorry, and then this is saying you have a like what's in this language is anything which has an equal number of zeros and ones, right? Now, since this one's saying, oh, we want all of our zeros and then all of our ones together, and that's regular. What we can do is we can say, okay, our new language is going to be the intersection of the strings that have equal number of zeros and ones and have all their like zeros and then all their ones. Now, obviously, the only string that's in here is 0 to the k, 1 to the k. And here we prove that that's not regular. So obviously, proof by contradiction, right? We know that B, this one originally is not regular. Because if you think about it, like all we did was combine it with more regular stuff, right? If B was regular, we combine it with more regular stuff. If the whole thing's irregular, the only thing that could possibly be true is that B is the thing that's making it irregular. Are you saying like why is this not regular or why is this? Yeah. So if you think about it, right, this is saying B intersection 0 star 1 star is just saying it accepts anything that is equal numbers of zeros and ones and has like all the zeros first and then all the ones, right? Does that make sense?
Yeah.
And you can kind of convince yourself that what this effectively just is this 0 to the k, 1 to the k, right? And we proved earlier that this is not regular. And we could do this on like this might be how maybe like something that happens on like an F or Q, maybe like he said like, okay, prove this is not regular, and then use it to prove that this is not regular. So good question. So B is what we like start off with. We want to prove that B is irregular, right? And so we do this by assuming it's regular, right? And then we apply, we make an expression, right? If B is regular and like this element here is regular and intersection is just like it's closed under like regularity, right? If you intersect two things together and they're both regular, the whole thing's going to be regular, right? We do that because then it lets us show that like what this is it's just 0 to the k, 1 to the k. And because this is irregular, we know this also has to be irregular. So yeah, essentially B by itself, maybe it's too difficult to prove through like pumping that's irregular. So we intersect it with this to make it equivalent to something that's irregular. And that lets us show that B must be the thing that's making the whole thing irregular because these things are regular. Does that make sense? Okay. Turing machines. I feel like we mentioned it and then like never talked about it again. So I honestly don't really know like what he wants us to do with this. Maybe it's just a simple multiple choice question at most, is all I can really imagine. Yeah, this stuff is a bit more important. But like this stuff, it's a head and a tape of ones and zeros. Like the head moves left and right, it can read and write. And the tape is like as long as you want. And it's better than a DFA because it can actually write. So like I think we said in class like it can recognize like A star, B star, C star, which like a DFA cannot. Okay. And like how you formally define them, right? You have just like you're right. That would be recognizable. What did it say in the slides? Ah, that's what it was. Yes. A to the K because DFAs can't count. So this, no. Yeah. So that is what can't be recognized by DFA. Yeah. And I think the idea where there was like you just iterate over it and you say like, okay, do we have all A's and then all B's and then all C's? And then if so, like iterate back through it, like scribble off one of the A's, scribble off one of the B's, scribble off one of the C's. Keep doing that until you've either scribbled everything off and there's nothing left on the tape to read, which means there's an equal amount since we did it one at a time for every single one, or if there's like stuff left to scribble on like two of them or one of them and there's not for the other, then it's unbalanced and we know it's not under this language. So that's how it can do that. And yeah, like the definition, it has like an alphabet on its tape. It has like an input, which I guess is like if you like scribble something out, you can like you would be in like here, but not here. And then it basically says, oh, at a certain state with a certain value, it can alter that value and then move left or right as well. And then it will either, so this is kind of leading into the next slide. If you give a Turing machine an input, it will either accept it, reject it, or loop forever. And this brings us to the difference between Turing decidable languages and Turing recognizable languages. So if you are building a machine to recognize a language, it's said to be Turing decidable, that language, if you can build a machine where you feed in an input. If that input is correct, it will output, we accepted it. If it's wrong, it just outputs, we rejected it. Always does that. So it's like a perfect decider, right? You input it, decide if it's correct or not. However, sometimes, for some languages, you can't quite do this. And you have to settle on what's known as like a Turing recognizable machine. And so, I guess it calls like a recognizer. So a language would be Turing recognizable if the best you can do is a machine that if you feed it something that works for that like language, it accepts it. But if you feed it something that doesn't work, it may just loop infinitely. Yeah. So here in this Turing decidable bubble, this is like the perfect machine that will always, you know, if it's correct, it will accept. If it's bad, it will reject. And then this is just like, sure, it will accept it if it's correct, but who knows what it'll do if it's incorrect. It may just loop infinitely. I think that's, I don't know. I don't know if like what else there really is there. Oh, okay. Yeah, I guess maybe know that like this is, yeah, I guess I would know this is the hierarchy, like it's stuff that's recognizable, and then like decidable is more niche in that, right? Not every language can be decided upon. And then also, smaller than that is all the regular languages, because like this, this is Turing decidable, but it can't be, it's not a regular expression, right? It can't be recognized by a DFA or an NFA. So yeah, I would know this hierarchy between the three things, I guess. Okay, we'll move back on to intractability, the last section. Do you have a question? Okay. This is just like P equals NP, that sort of stuff. Yeah. So just basic definitions. T is just the set of problems where there's a polynomial time algorithm that exists. So essentially you can solve the problem in polynomial time, right? Give me a graph, I'll give you an output to n to the whatever, right? NP is the set of problems for which there's a polynomial time certifier. So what that means is you have an answer, and then you can guarantee that that answer is a correct solution to the like original problem or not. And so the way they presented this in class is with this like certifier certificate idea, right? The certificate is essentially like a solution to a problem, or like the proof that goes alongside that solution. And then the certifier will take in like the input and that like certificate, and it'll say like, oh, does this certificate is the certificate like a valid solution to the algorithm for that input? I think it'll make a little more sense when we go over the actual like just some examples. So here, like, say we have something, see it, Ryan, that's input into the certifier. It'll just be like a number, and we want to know, is it composite? What we can do, we'll run the algorithm, and we'll take determine if it's composite or not. But the important thing is we get along with it like a certificate that that shows us like if it's composite or not. And so then we just see our certifier will just be like, oh, does this divide into this? Yes. So therefore it must not be a prime number, so it must be composite. And so the original thing was correct. It could also be, yeah, it's either or. I think the one that made it make sense to me is this one down here, the Hamiltonian path one. So we want to like say like, okay, we have a graph. Do we want to visit every node? or can we visit like every node with a simple path? So what this certifier gets, the S, the input, is just the graph, right? So the like actual thing you're running the algorithm on. And then T is like the sequence of nodes that actually forms the Hamiltonian path. So it's essentially like what the algorithm outputs, or I guess the algorithm output may be like a yes or no. So it's not always what the algorithm would output, but it would be like how the algorithm proves that that output is correct. So that passes into the certifier. And then the certifier, what it would have to do is it would have to check if that sequence of nodes, if that like is actually a valid sequence in the graph, and if that or if that like set of nodes visit every single node once. So we want to check like, is it actually a simple Hamiltonian path? And we can do that in polynomial time, which makes it NP total in totality. And I think the idea here is like, if you can pass in like a certain certificate, so like that will have the certifier say, oh, this is indeed the correct output, then you like know you have solved the problem. But if there doesn't exist a certificate for that graph, the certificate will, or the certifier will like say is correct, then we know that graph cannot have a Hamiltonian path. And then like 3 as well, the certificate here. So like this is the thing that's the S that's passed in, and this is the certificate. The certificate is just like the assignments to all the variables. And so the certifier will just be like assign, calculate. Oh, look, this is output true. So the thing is true. So we can check if this is correct or not, polynomial type pretty easily. You're saying this? So yeah, so for this, what it's saying is like, so what the 3-step problem is, right? This is like a logical expression, right? Of like 4 variables, x1, x2, x3, x4. We want to make it, or we want to know if there exists a assignment of x1, x2, and x3, and x4, where this whole thing will be true, right? So we've already run the algorithm, and we know that like these values make it true, right? So the certifier just checks like, okay, these values, does it actually make it true? Yes, it does. Okay, awesome. If it was like, if this was like true, when you run the certifier, it would be like, oh, wait, this will screw this over. And so then this whole thing is false. So this does not like work. This is not a correct solution to the variable or to the like equation. So essentially, yeah. So ultimately, what you want for the problem to be NP is a certifier that will always produce the correct output. Now, it's totally true that like for a certain instance S, right, there's like no possible way to like have a certificate that works, right? Maybe there's like, an extra variable or something, and then it complicates things or something, or no, there's probably like less variables here, and maybe for a certain S, it can't be true. But this, the certifier, if it's correct, no matter what like thing you pass in with alongside that S, it will always output false, right? Because it knows that like there's no way, or therefore there can't be any way to pass in a certain certificate that will work. So sometimes, certain like you can't have a certificate that's correct for a certain output or for a certain input. But the important thing is the certifier, when there is a certificate that works for a certain input that the problem can be solved on, it will say, yes, this is correct. So yeah, it just has to make the distinction. That's all. Okay. This is like a random thing he threw in. EXP is just problems for which there exists an exponential time algorithm, which hidden among here is probably like one of the most important things you should know for like writing proofs or whatever. If something is in P, it is in NP. So if you have a problem, I think like on the homework, there was like an interval scheduling problem. And we know we can solve that in polynomial time. Therefore, you can also check it in polynomial time. So this comes up later. If you ever need to prove something is an NP, if you can prove it's in P, you're automatically done. And then, and then here it was like, oh, if you can prove something is in NP, which means you can check like that a value is or if like an output is correct in polynomial time, you can solve that problem in exponential time, because what you can literally just do is every single input, run it, see if any of them work, and then if one of them works, there's your answer, right? So for like Hamiltonian path, you just take like every possible path and then try them all, and that will end up being an exponential time problem. So that will solve it for you. Okay, and then probably the most notable part, reductions. So you can, if you have a problem X, and you can essentially rewrite it or manipulate the inputs such that you can just run Y, and then Y gives you the answer for X, more or less. Then you can say that X reduces to Y. So like the formal thing is here is you have to have a polynomial number of calls to like an algorithm for problem Y, and a polynomial like number of steps to just kind of break things down into those calls to Y. So essentially, I mean, this is pretty straightforward. Like if you have one algorithm that solves a subproblem and it's polynomial, like you can reduce a certain problem to that smaller problem and the whole thing will be polynomial. If you have a polynomial number of calls, of course. And then, and if it's two-way reducible, then you say it's like polynomially, or it's equivalent. And here are some, I know it says NP complete problems, we're not going to worry about that yet, but here are some like problems to note. He'll probably give you these on the test. If they're like on the FAQs, he'll probably be like, oh, remember that an independent set is this. But these are the ones we discussed in class. Independent set and vertex cover, probably the most important. Independent set is like saying, okay, the things are over there. Independent set is saying, oh, if you have a certain number of vertices in a graph, you want no two to be adjacent. So that's just like what this is, right? No two red vertices are adjacent. Vertex cover is saying every single edge, there's a certain number of vertices where their edges, those vertices are adjacent to every single edge in the graph. So like these nodes, these black nodes, right? There's no edge that is not connected to one of these black nodes. So essentially these black nodes cover over like every single edge of the graph. So they are a vertex cover. And then there's set cover, which is like pretty similar to like, I think vertex cover. Yeah, and it's just saying like, if you have a bunch of elements, you have a bunch of subsets of those elements, how few of those subsets do you need to have that full range of elements? And then 3-set we looked at briefly here. It's just saying if you have 3 clauses of like ORs of like disjunctions and you AND them all together, there's 3, like it doesn't matter how many groups there are. It's just each group has 3 disjunctions, and then can you satisfy that? That's also a problem to be aware of. Okay, and then here's some like examples of the reductions and like the intuition behind them. So it's very likely, I think, that one of these like will be on the exam. Because at the end of the day, like this is kind of the main part of like what we need to know for this chapter, I guess. So first thing we went over, right? Independent set is equivalent to vertex cover. So remember that equivalent means you can reduce vertex cover to independent set, and independent set can be reduced to vertex cover. So first, independent set to vertex cover, right? How we can look at this. So say we have an independent set of nodes, right? here it's just going to be like these red nodes here. And we want to prove that the black nodes form a vertex cover. So how we can look at it is just saying like, okay, every single edge, because of the fact that like these are independent, that means no two red nodes can be next to each other, right? No two red nodes can be connected by an edge. Therefore, every single edge has to have at least one black node next to it, right? It needs to be adjacent to at least one black node. And then that's literally just the definition of a vertex cover, where the black nodes will be adjacent to every single edge, because there exists no edge with two red edges, or with two red nodes connecting. And then here's a similar thing the other way around. It's just saying, okay, if we have this vertex cover of black nodes, we know that every single edge has to be connected to at least one black node, and therefore two red nodes can't be connected, and therefore the red nodes are independent. And vertex cover can also be reduced to subcover. It's just like this diagram down here. Essentially, if you make a set where like each edge is a value, and then you group them by what nodes connect to what edges, by taking the nodes like that attached to certain edges, like here, F, we'd be taking this set. We can essentially like cross these off in our total set as characters to take, just like we cross it off as edges to take in our graph. And so effectively what that, does for us, we just essentially select edges like we do, select characters like we do vertexes, but we're just taking, or like we do edges, but we're just taking subsets instead of vertices. And then there's a really crazy one. 3 set can be reduced to independent set. I don't think he'll make you do something like this on the exam, because this is kind of bonkers. The idea here is like you have each of these, and then like each clause gets like connected together in like a triangle, and then each like negation is like tied to itself. And like the idea is like you can only, independent set means you can only add one of these 3 nodes to the independent set, but if you add like this node to the independent set, you also can't add its disjunction, because that would mean like, you're negating, you're choosing a element and its negation. And it kind of makes sense, because like the whole point is like we want these ors mean like we want one element from each of these groups to be true. So essentially we want to add one of these nodes from each of these groups to our independent set. But if we add a node to our independent set, we got to make sure that we can't add any of its anything that's like not it, because then that would just be like a contradiction. And so we do that by just connecting the nodes and saying, they can't be independent. So yeah. And the last slide is on NP completeness. So a problem is NP complete if every single other NP problem can be reduced down to that problem. No, yes, yes, yeah. Every other problem in NP can be reduced to that problem. And I saw someone post something like this on the Slack. It was like on the homework, it was like, prove that something is NP complete. And they said like, okay, well, to prove it's NP complete, we first need to prove it's in P, or prove it's in NP. And we do this by just proving it's in P, and therefore if it's in P, it's in NP, yada, yada, yada. If a problem is NP complete and it's also in P, then that means P equals NP. Because if every other problem can be reduced to that one problem, and that one problem can be solved in polynomial time, then every other problem can also be solved in polynomial time. So don't do this, because this, if researchers could not solve this over like hundreds of years, you're not gonna like prove this is true on your exam. So if you ever see this is like being proved, like backpedal, you've done something wrong. So this is like why, like, if you're proving something is NP complete, you don't want to try to prove it's NP because, like, it's not going to work for you. Like that's not going to that can't happen. But anyway, yeah. If one of them is NP, if an NP complete problem is NP, since every other problem can be reduced to it, all of them are NP. Yeah. 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 So good question. I'll cover that right now. So if we want to prove that a new problem is NP complete, right? First thing we have to do, first of all, for something to be NP complete, it's in NP. It has to be an NP. And like I said, you're not going to be able to prove it's an NP by being NP because NP is equal to NP. No, don't do this. What you want to do is just do what we did before. We'll prove it like it has the certifier that runs in polynomial time. But what you were asking, so what do you do from there? You have a problem that's in NP. How do we know it's NP complete? What we do is we have an NP complete problem that we know it's NP complete, and we have to reduce it down to that problem. So essentially, say we have like independent set. We want to like reduce it like independent set to that new problem. And the idea is there's like NP complete is like a problem to which all other problems can be reduced. So if you have like all problems, that means all problems can be reduced to like a independent set problem, right? So if all problems can be reduced to independent set, and you prove that independent set can be reduced to like your new problem, then that means, yeah, all problems can be reduced to your new problem, and therefore it's also NP complete. So that's how you want to do it. Yes, you have to do it in that direction. And I feel like that might be a little bit. Yeah. I got super confused as well at first. Especially with like the diagram and the slides, it's like it does it like the other way around. I got so confused. But yes, since NP complete means like every other problem is reduced down to it, you want to take a problem you know and reduce that down to your new problem. It does seem a little backwards. I don't think it's terribly intuitive, but yeah. I'll flip your question real quick. Say we're trying to like prove a certain problem is NP complete, right? So in that case, we'd reduce independent set down to that new problem, right? What we do is we'd say, okay, this is an independent set. We have a graph and we have a set of nodes that are independent, right? So with that, how can we prove that this this problem can be solved by representing it as our new problem? So like for here, when we reduced independent set to vertex cover, what we said is like, oh, we have a independent set, and then we therefore also have a vertex cover. Hold on, I think that's a bit confusing. Let me. What was that? The total minus the vertex cover going to be equal to your independent set. So which one you start? You start with the set vertex cover? Yeah. Let's do an example. Let's do number 17 on the homework. Now, I'm going to be real. I have no clue if my solution for this problem is correct because he did not post the solution to this problem. But we'll see. Actually, hold up, this is what I can do. Oh shoot, I can't. Actually, yes, I can. Whatever. Okay, can you guys see? I assume. Oh no, what up? Ah. So this was on the practice problems. Actually, let me share my entire screen so you guys can see my notes. Link. Okay. So yeah, this is how I solved. This is like where I'm really hoping I did not screw this up. But so this problem, number 17 on the homework, right? It's saying, so we have a directed graph, right? With like weights on its edges or whatever. Actually, I just realized that this might be a little uh, inconvenient because you might not know what the thing like proving from it is. But regardless, is this? Wait, can I annotate or something? Oh, okay. Yep. Okay. So this thing, basically, there exists we have to see if there exists a cycle in a graph so that the sum of edge weights on the cycle is 0, right? So that's our problem, and we want to prove it's NP complete, right? We're not going to worry about like this thing. This is just like proving it's an NP. I don't know why I crossed it out, but yeah, don't worry about that. So what we do is like, there's this problem they introduced called subset sum, where essentially you have a set of elements and you want to know if like any of these, like add those up, they equal a certain sum. So like if you add X amount of elements, any number of elements in the any number of elements in the set together, it will create a certain sum. So essentially, if there's a certain subset of elements that equal that certain sum when added up. And that's an NP complete problem. So we want to prove that this one's NP complete, which means we need to start with an NP complete problem, and we reduce it down to this problem, right? So what I did. So we start with an instance of the subset sum problem. We want to solve subset sum. Say we have a set of elements, 1, 2, 3, 4, for instance. What we do is we want to convert these to an input to the zero weight cycle problem, and then run the zero weight cycle. And then we can use the output of the zero weight cycle to determine if there's to determine the output to the subset sum problem, right? So because we're reducing subset sum down to zero weight cycle. So we start with an input to subset sum. And then what I did, I have no clue if this is right, but this is kind of what I thought of. So if you, obviously the zero weight cycle, it inputs in a graph, right? So we need to somehow convert this into a graph that will like, yeah. So that will work with zero weight cycle and reduce down properly. So what I did is if you have like a subset sum, you want to determine if like any of these elements like equals 0 total. Obviously they don't. I'll make it like -3. So some of them do. So what I did is I accounted for like every single possible cycle. So essentially here, man, now you can't see this, but here, essentially I see like, okay, if you can add every element in the set together, right? This four-pronged thing, four-edged thing will form a negative cycle, correct? If you can add 3 of the elements together, then like this will form a negative cycle. If you can add 2 of the elements together, like this will form a negative cycle. And if you can add if one of the elements is just 0, then like this will form a negative cycle. And this represents like a node where it's like the edges are like 1, 2, -3, and 4. So essentially this is saying like, oh, is there a single element that creates a negative cycle? And then you could be like, oh, are there 2 elements that create a negative cycle? Well, how do we check this? Well, we'll have to go like, oh, 1, 2, -3, 4. Oh, wait. Oh, okay, that was the zoom window. Like, how did I just change what was being displayed on my desktop or my laptop? And then so on and so forth. So this will show if there's a, negative weight cycle that's 2 elements long, or a 0 weight cycle that's 2 elements long. And I think I ended up being like, oh, you don't actually need like a few of these. Like you can optimize it a little bit, but yeah, essentially to answer your original question, sorry. If we're reducing an NP complete problem, the subset sum, to our new problem, the 0 weight cycle. So what we do is we say we start with an input to that subset sum problem. We want to show that we can change that input to the subset sum problem to an input for that 0 weight cycle problem, and then show that when you run the 0 weight cycle problem, it will then output, that output will also be correct for the subset sum problem. Yeah.
So is that first one you had before, is that the one that's given as MP3? Like, so
yeah.
You just take that, right?
Yeah. That's exactly what it is. Yeah. So, yeah, exactly. Yeah, you're saying like, okay, I have an input to an NP complete problem, right? Can I solve this NP complete problem by warping the input, reducing it to this other problem, then solving this other problem, and then just outputting that? So yeah, yeah. Yeah. I mean, you would have to like deal with like cycles and stuff, but yeah, essentially, yeah, if you took the graph and then somehow converted that to like a set, that would be incorrect. I think in that case, you'd have to like find every cycle in the graph, and then like every cycle, you'd have to run subset sum on its own or something. But again, you get the idea. Let me actually pull back up the slides. So like, yeah, here, I think this is another good example. This 3 set problem, right? We're saying 3 set can be, I think this is the thing, can be polynomial time to reduce the independent set. So what do? We input, our input is like this 3 set problem. And then what we do with that input is we convert it into a graph, and then we run independent set on this graph. And if independent set is like the independent set for this ends up being like giving us the output for the 3 sum problem. Make sense? Okay. Yeah. Yes. Okay. In the yeah. I'll go over it just in case. In like that one example, right? From the textbook, right? We have like a set of elements, right? And this is our NP, this is subset sum. This is our NP complete problem, right? And here we're reducing subset sum to our new problem. And then in the other example, we had 3 set, and we wanted to reduce that to our new problem. So what we did was we, just like here, where we're taking in an input to subset sum, we took in like an input to 3 set, Yeah, and then both of them, we like make a crazy graph or something, and then we, use that. Because yeah, both of these new problems were like problems that could be represented uh, with like a graph.
One of the slides you were showing how like during the proof, to make sure that we don't show like percent, you have to like set show like all certifier, like how would you ask?
Yeah, yeah. So that is like what we went over here. So say you're given something and it's like, oh, prove Hamiltonian path is NP complete, right? Maybe it's not. It probably is, let's be real. Because we went over it. But first thing you'd have to do is prove it's in NP. So what you would do is you would do something like this, where you would say, oh, if we have a certifier that like, if it's given the certificate, we'll just like do this, like check that the certificate is actually a simple path, more or less. Then like if we can show that runs in polynomial time, then the whole thing will. Yeah, essentially, if you can design an algorithm to check if a certificate solves a problem in polynomial time, then it's an NP. And that's how you're going to be doing it. Let's see, how did I do this one from the homework? Did I write it out? Yeah, so like the one on the homework. Yeah, here. Like the zero weight cycle thing, right? We need to like to prove it's NP complete, we need to prove it's an NP. So what I just said was like, oh, we have a certifier, and the certificate is just the series of nodes, the cycle in the cycle that form the zero weight that have like some zero weight. And then we just have to check that they do form a cycle in the graph and that is a weight, is like weight zero total in total. And then that would verify if that is in fact a correct solution or not. And that obviously just runs a polynomial time, so it's NP.
How is that zero cycle?
Sorry, what are you talking about? Oh, yes. Okay, sorry. That was like that like example thing. So like that one doesn't actually have a zero weight cycle. Yeah, that this is just like an example. If I had like, I don't know, because these don't none of these have a zero weight cycle because none of these elements in the original problem in the subset sum can be added up to be zero. So yeah, essentially you run the thing on this and then on this and then on this and then on this.
I didn't put
Like fully connect everything. Oh, I think that would work too. Yeah, yeah.
that would just it's only like one.
Although, would you risk taking like multiple like nodes multiple times? I don't know, but I think that seems to work as well. That seems to be the easier way to do it. Yeah, that actually probably is the easier way to do it. It was make a simply for Zoom. It was make a fully connected graph and then just run zero weight cycle because yeah, I think that's probably the way to go. Okay. Anyone have any questions or want to go over anything? Just chat messages. No, there's not. All right. If not, I'll see you guys. Good luck on the exam on Wednesday.